Hello, everyone. This is the lecture for Friday, April 3rd. Okay, we're going to finish off this stuff about bivariate distributions. I do apologize for the tardiness in getting this out. It's been it's been a day for sure. Remember that there is a quiz due on Friday. So just make sure that if that's on your radar screen, upload that at the appropriate time into Canvas. Just want to make sure that you're apprised of that. Now, one of the last things I want to talk about, I might go into depth about a couple of things with the theory of probability, folks, but as it pertains to this particular lecture, I just want to cover the high points. And maybe I'll take a deep dive later with those folks, but I just want to finish this stuff off with multiple dimensional continuous distributions. And we're just going to do two variables because that, frankly, that's enough. You can do higher dimensional ones, but if you can understand two variables, that's typically enough to give us what we need. So remember last time we talked about the joint probability density function, f of xy. And really it's a function of two variables, okay? And this time they're continuous variables, x and y, not just discrete ones. And this is a density. So the values of the function itself are not probabilities. But when you integrate, this time not over an interval of values, but over a region of values. So, you might have an interval of possible values in x and y, and you basically have to do two integrals back to back to get probabilities related to this density function. The picture down here is of one of those situations. You could think of the graph of f of xy as a surface that has two variables of input and one variable of output. Okay, so the two variables of input come from the xy plane in the region A, and the one variable of output is the function value f of xy there. Okay, and you need to integrate all of those function values over the region A if you want to get the probability that the random variable or the random vector, actually, random ordered pair x comma y belongs to A. Okay, so last time we talked about what properties we would expect this thing to have, namely if you integrate over the whole real line in both the x and the y variables, you should get 1. This thing ought to always be equal to or greater than 0, whatever x, y is. This thing has no business ever being negative, okay? In some sense, if I go back to this picture, really the probability, remember in the one variable case, the probability corresponded to area under the curve f of x. Now it's the probability corresponds to the volume under the surface f of xy. Okay, the volume between the xy plane and the surface itself is the probability. Okay? The way you get that volume is by double integrating this function. Okay, so also if I want the marginals, the x marginal, I just integrate out the y variable. That's kind of like what I did in the discrete case. Over there, we simply just added up all the y values for a fixed x value, and that was our marginal. Similarly for the y marginal. Okay, so those are the marginal densities, if you will. And independence. How in the world would we talk about independence? Well, again, remember back in the discrete case, P of xy, that was the probability of x equaling x and y equaling little y. And independence would happen if and only if that equaled the probability of the product of x equaling x and the probability of y equaling y. So back then, and we saw that P of xy, the joint distribution for x and y, if x and y are independent, then that would be equal to the marginal of x at x times the marginal distribution of y at y. And the same thing is true in the continuous case. You have to go down to the level of the density. Just like over there, you had to go down to the level of the probability mass functions. Here you go down to the level of the density. The probability mass function is the thing that you added together to get probabilities. The density is the thing you integrate to get probabilities. And you capture independence in the same way here. The density of x and y had better be equal to the product of the marginals. That is what it means to be independent, for x and y as random variables to be independent. The joint distribution, or the joint density would have to be the product of the marginals. If anything else happens, you say that x and y are not independent, i.e. dependent. Okay, let's do this little example here. Okay, Annie and Alvy have agreed to meet between 5 p.m. and 6 p.m. for dinner at a local health food restaurant, Let X be Annie's arrival time and Y be Alvy's arrival time. Suppose that X and Y are independent, with each uniformly distributed on the interval from 5 to 6, okay? Okay, that tells us something, incidentally, about what the individual distributions of X and Y are, okay? It's asking here what the joint PDF of X and Y are. Well, we're assuming that X and Y are independent. And incidentally, 5 is, 5 p.m. and 6 is 6 p.m., okay? So some of the computations we're gonna do here, we're gonna have to kind of think about it in context here, because here we're going from 5 to 6 on the number line. So like 5:15 p.m., that corresponds to 5 1/4 hours, right? So that'd be 5.25. And 5:45, which we see in part B, that just corresponds to 5.75 in that interval. So you have to do some translation back and forth there, okay? So we want to answer a few questions here. One of them is, what is the joint PDF of X and Y? Okay, that's actually, that's fairly easy. I think I'm going to actually write that right here in the slideshow itself, but the other ones I'm going to have to go into a whiteboard mode here and talk that through. So let's look at this. Let me turn on my pen. Okay, so what is the marginal? Okay, what is the marginal distribution for X? Okay, well, it's uniform on 5 to 6. And you know that, remember, if it's a uniform distribution, it has to be 1 over B minus A. So in this case, that's just 6 minus 5. So really, that's just 1 if X is between 5 and 6, okay? And it's equal to 0 otherwise, okay? And by the way, Fy of y is just, it's the same thing. It's equal to the x marginal, let's just replace x by y though, okay? So the y marginal is exactly the same as the x marginal. And what is the joint PDF of these? Well, x and y are independent. So f of xy is going to just be the product. It's going to be the product fx of little x, fy of little y. And by the way, what's that equal to? What is that equal to? Well, think about it for a minute. If I'm multiplying these things together, it's just going to be 1. Okay, so think about this. This is going to be 1 if x is between 5 and 6, and y is between 5 and 6. After all, this is a function of both x and y, and it's 0 otherwise. 0 otherwise. Okay, so there it is. And we'll graph the thing over there. So look at this. The last two questions are, what is the probability that they both arrive between basically 5.25 and 5.75, right? A quarter of the way past the hour. So they both arrive at a quarter of the way past the hour and a quarter of the way before the next hour, 6 o'clock. So basically that means both X and Y have to be between 5.25 and 5.75. And the last question we're going to answer is if the first one to arrive will wait only 10 minutes, right? So whoever arrives first is only willing to wait 10 minutes for the other person before leaving to eat elsewhere. What is the probability that they both have dinner at the health food restaurant, right? So that's another question we're going to answer here. Okay, so let's head on over to this other thing, and we'll work a little bit over there. Okay, here we go. All right, so once again, let me kind of make sure I'm in an acceptable color here. I have the joint density, which is equal to 1 if X is between, let me write it this way so it's easier to see. Oops, not 0. X is equal to or greater than 5, and so is Y. Okay, and both of these are equal to or less than 6, and it's equal to 0 otherwise. Okay, so what does the graph of this thing look like? Well, watch. Okay, I'm going to draw a little three-dimensional graph for us here. This is the x-axis, this is the y-axis, and this is the z-axis. Okay, and in this direction, we have positive x values, we have positive y values, and we have positive z values up here. Okay, so in other words, right, I mean, these dotted lines that I'm putting in here, those are the negative x, y, and z values, respectively. Okay, so 5 and 6. Let me change colors here a little bit. Maybe I'll use blue. Okay, so let's say that 5, I don't know, 5 is like right here on the x-axis, and maybe 6 is right here. And then over here, maybe this is 5, and this is 6. Okay, then okay. All right, so those are the x values between 5 and 6. Okay, so like this little square of values are where I actually get something other than 0 for the function. Okay, so let me change colors here, and I'll start drawing this thing. So at anywhere above this little blue square, I'm going to get a function value, and it's going to look like this. And what is the height of this thing? 1. Okay, so that's our little surface right there. Okay. Okay, so let me just kind of color in that surface right there. So that is the graph. Okay, so that's the graph of z, right? So it's the graph of z equal to f of x, y. Okay, so that's the density graphed right there. So they wanted to know the probability. Okay, so let me use some red pen here. Okay, like this. They wanted to know the probability that they both arrive between 5:15 and 5:45. That means 5.25 and 5.75. Okay, so that means 5.25 is less than or equal to x is less than or equal to 5.75, and 5.25 is less than or equal to y is less than or equal to 5.75. Hey, and I can kind of look at this over here and say to myself, all right, well, 5.25 and 5.75 are basically right here. Okay, so let me just kind of say this is 5.25, and this right here is 5.75. Okay, And similarly, I could do the same thing over here, okay? And if I were to go out here and kind of extend this through and do the same thing over here. Okay, I'm talking about this little area right here. And technically speaking, I need to go up to the surface itself and compute the volume of this thing. Okay, that's what I'm trying to compute, right? So this is, I need the volume of this. So this thing is equal to the volume of that red prism, okay, which is equal to, okay, so let's see here. What is that going to be equal to? Think about it for a minute. It's going to be the area of the base, and the base is just a square in this particular case, and the height, of course, is 1. Okay, so the base and the base length and the width, the base and the width, the length and the width at the bottom, what is that? That's going to be half a unit and half a unit, right? So it's going to be 1/2 times 1/2 times the height, which is 1, which is 1/4. Okay. Another way that we could have done that, by the way, is we could have gone the probability of 5.25 being equal to or less than x equal to or less than 5.75, and the same thing happening for y. Well, look what we could have done is we could have said this is equal to, right? This is because x and y are independent. If x and y are independent, then this is just going to be the product of these things. It's the probability of 5.25 being equal to or less than x being equal to or less than 5.75 times the probability that the same thing happens for y, but that's the same probability, right? So I can basically just square that. And what's the probability that x is between 5.25 and 5.75? Well, that's like half of its values, right? Total, it has a width of 1 that it can go through, yeah? And so this is half of its values. So this would just be 1/2 squared, which is, once again, 1/4. And there's kind of a third way that we could do this, okay? We could actually use the density, okay? So the first way, we kind of use geometry right here. We use geometry to pull this off, okay? So we used geometry. So this way right here used geometry. Okay, here we used independence, okay, and just the marginal things, but we could have also done integration, okay? So let me, please permit me to use some shorthand notation here. I could go the probability that 5.25 is less than or equal to, rather than, so I don't have to write it twice, I'll say both x and y are bigger than or equal to 5.25, and they're both less than or equal to 5.75. And I could actually double integrate. So watch this. This is the integral of the integral, okay, of what? Well, it's going to be 5.25 to 5.75, and then 5.25 to 5.75. And I would do the f of xy, which is 1. And then I have to decide if I want to do dx or dy. You know, it doesn't really matter. Let's just do dy and then dx, okay? And the way that you do this, just so that you recall, is you do like the innermost integral first, okay? And if you do the innermost integral first, it's going to be y evaluated between, right, the antiderivative of 1 dy is just y. I would plug in 5.75, 5.25 and get 1/2, okay? And then you would do the once that number, you have that number, you can pull it out, and then you would integrate the other one, 1 dx, and you would get another 1/2. So again, this would be 1/2 squared, which is 1/4. Okay, so this is a way that you can do it using just using integration, double integration, okay, just to make sure we're all on the same page here. Okay. So the other problem that we were supposed to do, okay, just to keep on trucking here, the other thing that we were supposed to do was we were supposed to compute the probability that, so if the first to arrive will only wait at most 10 minutes, what's the probability they meet? Okay, so like if one of, if one of them arrived exactly at 5 o'clock, then the other person had better get there before 5:10. Okay, so whatever happens with the first person, the other person had better not be there any later than 10 minutes after that. Okay, so yeah, so how would we get that? That seems like it might be kind of tricky to pull off. Okay, so let's see. Yeah, so how would we do this? Well, we would want the probability, and actually, because you could exchange the roles of X and Y, really what we want is 2 times the probability. I'm going to go ahead and assume that, I'm going to go ahead and assume that X is less than Y. So X is the first person to arrive. Okay, so it's going to be 2 times the probability that X is less than Y. So Y arrives after X, but no later than 10 minutes after X. Okay, well, what's 10 minutes here? Okay, remember, we're on a number line. Okay, and you can't put plus 10 because the number line is only 1 unit total. 10 minutes corresponds to 1/6 of a unit. Yes, because that's 1/6 of an hour. So, okay, so it's going to be X plus 1/6. Okay, so that's what's going on. Why is it 2? Well, because I could just as well have had Y arrive first, and then it would be X, or it would have been Y less than X less than Y plus 1/6. Okay, so X gets there first and is only willing to wait 1/6 of an hour. Okay, and therefore Y had better arrive exactly in that interval, and I have to double this. Okay, so, yeah. So first of all, what are we going to do? Well, there's a couple ways we could do this, but let's actually try to do it with integration. Okay, so what values of X should I go between here? Okay, well, so well, X could literally be anything. X could literally be anything between 0 and 1. Or sorry, not 0 and 1, between 5 and 6. Okay. And what's going to happen here? Whatever X is, okay. Okay, so what I'm doing here is I'm going to have dy dx, okay? And we're going to be integrating the function 1. So what is going to be happening here? Y, okay, so this innermost integral here, okay, which is this one, okay, this is an integral in Y. What values can Y travel between? If I give you an X value between 5 and 6, if I give you an X value between 5 and 6, what can what can Y travel between? Well, Y is going to go from X, okay, to X plus 1/6. To X plus 1/6, okay? And incidentally, if you If you think about this for a minute, uh, I think that, well, yeah, let me just sort of leave it at that for a minute. Okay, so what's going to happen here? So this is equal to, okay, 2 times the integral from 5 to 6. Okay, what is the antiderivative of 1? Well, that's y. Okay, so let me just write it like this. This is y evaluated between x and x plus a sixth, okay, dx. Okay, because the antiderivative of 1, remember this variable right here, right, this d whatever is telling me what variable we're integrating in. Okay, so you're going to plug in x plus 1/6 and you're going to subtract x. Okay, so this is 2 times the integral from 5 to 6 of what? Of 1/6 dx. Okay, well, what is the antiderivative of that? So let me just kind of write this. So 2, so look, there's 2, there's a 1/6 right there. I can actually pull this out. I'm going to end up with a 1/3 the integral from 5 to 6 of 1 dx. Okay, and I get a third. Okay, I get a third here. Okay, but actually there is a problem here. Okay, you have to be careful when you do these kinds of things, because remember, x and y have to be between 5 and 6 to contribute anything at all. Remember, the density only was something other than 0 if x and y were between 5 and 6. Okay, so as we let x travel between 5 and 6, there are going to be times when x gets large enough that x plus a sixth is actually greater than, oops, I put 5, but I meant 6 right here. What if x plus a sixth is greater than 6? Okay, if x plus a 6 is greater than 6, then what in the world am I doing letting y go all the way up there and acting as if this function should still be 1 right here? That's not allowed. Okay, so we have to be very careful here. This is not an accurate answer here. This is not an accurate answer. Okay, this is this example is intended to show you the sorts of things you have to be careful of, even in simple situations when you have multiple variables floating around. Okay, so here's a little picture of what I mean. Okay, so here we go. So this is what this right here, the red. Okay, let me just kind of draw a picture. So the red solid, the volume of the red solid is equal to the probability that x, right? So x comes first, and then y, so like think about this for a minute. Whatever x happens to be, if this is x right here, okay, then x, okay, so here comes x in here like this. Okay, this right here is the line y equal to x. Well, y has to start at x and go up to x plus a sixth. Okay, so I've kind of marked off the line y equal to x and y equal to x plus a sixth right there. So that's where y would reside, would be between those two things. And then of course, I would get these little slices like this. Okay. Right, I'm just really obsessed with this picture here. I would get these little slices like this. And so you see that you're going to get the volume of this red looking solid right here, this red solid. And it's not like a perfect, it's not like a perfectly shaped prism or anything like that. It's kind of got a trapezoidal looking bottom. Okay. So how in the world am I going to find the volume of that thing? Okay, so this is the problem. That red solid is the probability that x is less than y. Y starts at x and goes on up, and it's less than x plus a sixth. okay? That's what that probability is. But look, everything kind of changes right here, okay? Everything kind of changes right here, okay? What is that X value where that happens? Well, it's pretty easy to figure out that that's 5 and 5/6. So that's 5 and 5/6, okay? And then beyond that, Y starts going between X and just 6 at that point, okay? So because Y is 0 beyond 6, okay? So you start having to do something slightly different at that point. So let me just say, okay, that I really need to compute this. I really need to compute this probability differently. And remember, I still need to multiply this by 2 in the end. But how does this work? Well, I'm going to go from 0, or not 0, sorry. I'm going to go from 5 to 5 and 5/6. Okay, 5 to 5 and 5/6. And then I can just do what I did before. Then X and X plus a sixth is guaranteed. If Y is between there, then 1 really is what f of xy is equal to. So this is dy dx, okay? But that's not all, okay? Because if x is between 5 and 5/6, if x is between 5 and 5/6 and 6, then what is happening, okay? No, something slightly different. So if x is between 5 and 5/6 and 6, then what is happening? Well, y, okay, y starts at x and goes up to where? Well, it goes up to 6, okay? So that's just 1 dy dx. And now we just have to do this computation carefully, okay? So we do this innermost integral first, okay? So what's that going to be? Well, once again, it's going to be y, and you're going to go x plus a sixth minus x, okay? So it's going to be x plus a sixth minus x is just going to be a sixth. So this would be the integral from 5 to 5 and 5/6 of what? Of just a sixth dx plus, okay, what about this other one? Well, it's going to be the integral from 5 and 5/6 up to 6 of, right? So what's that inner thing going to be? It's going to be the integrals and antiderivatives y, and it's going to be 6 minus x, okay, dx, okay? So what does this end up being? Well, that first integral is pretty easy to compute. Let me just kind of go over here. That first integral is easy to compute because it's just 1/6 x, and then I have to take the top number and the bottom number and subtract them. That's going to be a sixth. So this is 1/6, right? 1/6, and then, well, actually, the top number by the minus the bottom number is going to be 5/6, actually. So it's going to be 1/6 times 5/6. Okay, and what about the other thing? Well, what is the antiderivative of 6? Well, that's 6x. And then I'm going to plug in 6 and 5 and 5/6. What's the difference between 6 and 5 and 5/6? Well, that's a sixth. So it's going to be plus 6 times a sixth. Okay, and then what's the antiderivative of x? Well, that's 1/2 x squared. This is going to be minus 1/2. Okay, and then it's going to be minus 1/2, and then it's going to be x squared. So that's going to be 6 squared minus, okay, 5 and 5/6 squared. And this is where I probably need to say 6 times 5 is 30. It's going to be 35/6 quantities squared. Okay. And that, my friends, is the true probability. So what is the probability that we wanted? Okay, and by the way, so that's just some kind of number. The probability that we wanted on the other screen, okay, was twice this. So this was the probability that x arrives first and y, right? So this is the probability that x arrives first and y happens to get there in time before x actually leaves. Okay, so I just wanted to show you this because you do have to be fairly careful when you work with these multi-dimensional, nuanced bivariate distributions. Okay, so there you go. Okay, in the interest of time, I think I'm going to forego doing this one. It's not all that unlike the one I just did, okay? But I want to get to some other applications here. So here's a nice problem. 2 light bulbs for a particular lamp. X is the lifetime of the first bulb, Y is the lifetime of the second. Okay? And but by the way, each of these are in units of thousands of hours. So, you know, like X being 1 would mean 1,000 hours, and similarly for Y. Okay? Lifetime, lifetime measurements are often very well represented by exponential distributions. So we're going to assume that both X and Y are independent. Okay, that makes sense that they would be if they're separate light bulbs. Okay, and they each have the exponential distribution with parameter lambda equal to 1. Okay, all right. So, and remember, lambda equal to 1, that means 1,000 hours. Okay, so let me just kind of say that. So this 1 right here really means 1,000 hours. Okay, because these things are in thousands of hour units. What is the joint PDF of these? Now we say PDF here because okay, so the joint probability density function of these. So what's going on with these things? Well, okay, what is the marginal? So fx, little x. Now you may recall that this is like, lambda e to the minus lambda x for x equal to or greater than 0, and it's 0 otherwise, right? And in this particular case, since lambda is 1, since lambda is 1, this is just going to be e to the minus x for x equal to or greater than 0. And of course, f, right, the y marginal is also e to the minus x. Or sorry, e to the minus y. And that's for y equal to or greater than 0. Okay? So what is the joint probability density function for these? Well, it's going to be f of x comma y equals the product of these two, because x and y are independent. Okay? So what am I going to get here? That's just going to be e to the minus the quantity x plus y. And that's for x and y both being greater than or equal to 0. Okay, both being greater than or equal to 0. Okay, you can kind of imagine what this graph is going to look like. Remember, it's a surface in 3-dimensional space. Remember, you had this kind of exponential decay in each direction. And you can almost imagine a surface kind of doing the same thing in this particular case. And we'll see that in just a minute. But the joint PDF is just the product of those marginals. Okay, a couple of questions here. What is the probability that each bulb lasts at most 1,000 hours? Okay. And what is the probability that the total lifetime of the 2 bulbs is at most 2? Okay, so the probability that each light bulb lasts at most 1,000 hours, that each bulb lasts at most 1,000 hours. And okay, that's fairly easy to compute just because we have independence here. Okay, this is asking for the probability that each bulb lasts at most 1,000 hours. Okay, so that means that x is less than or equal to 1 and y is less than or equal to 1. Each one lasts at most 1,000 hours. Okay, and by the way, that's just going to be the probability, because we have independence here. That's the probability that x is less than or equal to 1 times the probability that y is less than or equal to 1. So that means I can basically just square this thing, because they have the same distribution, both x and y do. Okay, and do you remember? Okay, and so this is equal to capital F of 1 squared. Do you remember what the PDF or the CDF, sorry, of this thing is? So what is f sub x of little x? well, that was like e to the minus, or sorry, actually, it was, let me erase this. Okay, so it was 1 minus e to the minus lambda x, but lambda is just x in this particular case. Okay, and that was for x greater than, or actually that was just for all x. Okay. Yeah, so actually, I should write that down. I should say that this thing is equal, that this is for, okay, so if you plug in 0, you have 0, okay? And, right, so this is for x greater than or equal to 0, and it's 0 before 0, okay? Otherwise, you're gonna get some kind of crazy nonsense. So that's for x greater than or equal to 0. So what's f of 1 squared? Well, that's just, if I plug 1 into this, it's gonna be 1 minus e to the minus 1 quantity squared. Okay, so there's one way that you could do this just using independence itself, yeah? Okay, you could have done this also by taking the joint density and integrating that joint density for x between 0 and 1 and y between 0 and 1. Yes, that would have given you the result as well. Okay. What is the probability that the total lifetime of the two bulbs is at most 2? The total lifetimes of both of the two bulbs is at most 2. Well, actually, x plus y, you think about it for a minute. Do you remember? So if x is like the waiting time for the first bulb to go out and y is the waiting time for the second bulb to go out, it's almost like 2 observations. You're waiting for 2 observations with parameter 1, okay? So where the length of time for 1 observation is 1 over lambda, where lambda is the Poisson parameter. Do you remember all those connections? So this is actually going to be distributed as the gamma distribution. How many observations am I wanting to have here? Okay, so it's going to be like alpha equal to 2. Okay, and remember beta, which is equal to 1 over lambda. Okay, what's 1 over lambda in this particular case? What was our lambda? 1. Okay, so this is just 1 in this particular case. Okay, so what is the probability that the total life of the two bulbs is at most 2? Well, here I'm just asking for the probability. And by the way, 2 means 2,000 hours. Okay, so this is the probability that x plus y is less than or equal to 2. Okay, or less than 2 would have been just as good. And how in the world would we compute that? Well, we could go use the gamma distribution in Excel. That would be one way to pull it off. So let's go do that now. Okay, here we are over in Excel. So let's check this out. Remember x plus y. X was the life of the first bulb. Y was the life of the second bulb. Each of those were exponentially distributed. And remember, if you have a sum of exponentials, that's just like waiting for one observation and then waiting for the other observation. The sum of those two is just going to be the gamma distribution, where you're waiting for 2 total observations. And in this case, I'm using A for alpha and B for beta. And beta is 1 over lambda. Okay, remember beta was going to be the expected waiting time, okay, for 1 observation. And that's always 1 over lambda. We talked about that before. So how do I do this? I'm going to go equals gamma. So here's the gamma distribution. What's our x, the thing we're going up to? Well, that's 2, okay? Remember, that means 2,000 hours. What's alpha? Well, 2. What's beta? 1. Do I want it to be cumulative? Yes, I do. Okay, and I get basically a 59.4% chance of that happening. That's about a 59.4% chance. And that, I guess that kind of makes sense, doesn't it? Because, you expect, right? So the average time for each one of the bulbs was basically, the average life of each one of the bulbs was basically 1, okay? And now, what are we doing? Actually, so the average life was 1, right? Because that's 1 over lambda. And now what are we doing? We're waiting for 2 of those to occur. Yeah, so for 2 of those things to go out. So you expect that probability to be pretty high overall, because 2 means 2,000 hours, where the average life for each one of those was 1,000 hours. So it's not that surprising that this probability ends up being about 59.4%. That should make sense to us. Okay, in the interest of time, I think I'm going to skip the next couple of examples here. One of them is kind of a conditional joint distribution. And you can deal with that similarly as you did in the case of discrete ones, but I'm more interested in you knowing how to deal with discrete ones. Those come up way more often. So I'm going to skip this one, and I think I'm going to skip this one as well, but I do want you to be well familiar with this guy right here. Okay, let's do these last 2 examples. So let's see here. This one says it gives me a potential density, a joint density for 2 random variables. Okay, and it wants me to figure out what this constant C is here. Okay, so what should be true about this? Well, we should have that 1 is equal to 1 equals what? What would happen if I integrated this thing over all possible values? Okay, so it looks like x is going between 0 and 1/2. Okay, and so that means that x is on the outside here, so dx. Okay, and on the inside is dy. Okay, and by the way, okay, so let me just, so what does y go between? Well, x squared and x. Okay, and I can factor out the constant, and then on the inside here it's x, y. And by the way, when you integrate with respect to y, x is like a constant, so you could like factor that out even. So this would be c. You can't factor out of the whole thing though, because x is still worked on by that last integral. That last integral is in the variable x. But as far as y is concerned, x is basically a constant. Okay, so it's going to be c times the integral from 0 to 1/2, and this is going to be x times the integral from x squared to x, y dy dx. Okay, so what is the antiderivative of y? Okay, so let's see here. So I get 1 equals, okay, so it's going to be c. The antiderivative of y is 1/2 y squared. So let's see here. Integral from 0 to 1/2. Okay, so it's going to be 1/2 y squared x times 1/2 y squared. I need to be very clear about what you're plugging in for here. So this thing is going to be evaluated between x squared and x dx. Okay, and so what do we get? So that's going to be, let's pull out the 1/2. Okay, so this is c over 2. And I am going to get x squared minus, let me just write this down, integral from 0 to 1/2. It's going to be x squared, x times x squared minus x squared squared, which is x to the 4th dx. Okay, so this is equal to, so let me just pull down the 1. This is c over 2. And what am I going to get here? Well, it's the integral from 0 to 1/2. And this is, if I distribute this x through here, I'm going to get x cubed minus x to the 5th dx. Okay, so I get 1 equals c over 2. And what's this going to be? 1/4 x to the fourth minus 1/6 x to the sixth. Okay, evaluated between 0 and 1/2. Of course, the 0 doesn't contribute anything, but the 1/2 does. Okay, so I get that 1 is equal to c over 2. That's going to be 1/4 times 1 over 2 to the fourth, 1/2 to the fourth, and minus a sixth, and that's going to be 1/2 to the sixth. Okay, and it's easy to solve for c at this point. I'll kind of leave that up to you, but solving for c is not hard to do at this point. So the whole goal was to figure out what c could be to make this into a density. And so we just had to set this equal to 1 and then do the integral properly to pull that off. Okay? All right, so there's that one. And this last slide here, I just want to stare at this for a minute together and kind of talk this through. I say, okay, let f of xy equal to this cosine thing right here with a constant, okay, where x and y run wild between 0 and pi. So that's, and you know, I guess the question is, could this even be a joint PDF for x and y? Could it be a legitimate thing? Well, the problem is there are some times on this interval, for instance, like if x and y are both 0, you get cosine of 0, which is 1, right? So if I plug in 0, okay, so note f of 0, 0 is equal to, right, what's the cosine of 0? Well, that's 1, so this is c. And remember, this thing would have to be greater than or equal to 0, right? Remember, the requirement on f of xy is that f of xy needs to be greater than or equal to 0 all the time, yeah? Well, are there some other values where that doesn't happen? Well, how about this? What if I plug in 0 for x and like, I don't know, pi for y? What is, okay, that's going to be the cosine of pi. You realize that the cosine of pi is -1. So that equals negative c, right? Negative c. But this already said that c had to be bigger than or equal to 0. And now I get the negative of c, so that needs to be less than or equal to 0. So those two things together tell me that c would have to be equal to 0. And so there is no way to make this work out. Okay. Problem is you have potentially negative values of this function that mess things up. The constant can't be chosen, you know, so that it turns the positives, keeps the positive stuff positive, and then turns the negative stuff positive later on. Okay, that doesn't work out for us. So this cannot be a PDF. Okay, so hopefully that at least gives you, you know, a nice refresher on some stuff with integration. Maybe you are rusty with multiple integrals, or maybe if it's possible, you maybe haven't even seen some of that before, but hopefully that kind of made sense, what was going on with some of that. Even if you haven't taken multivariate calculus before, a lot of this stuff is straightforward enough, and the ways we're going to be using this straightforward enough that it's not too bad to just kind of crank through it. Okay, I think that's all for now.